Welcome, friends. So, in the last class, we have seen few important aspects of long transmission line, that is propagation constant, characteristic impedance, and Ferranti effect. Now, in this class or in this lecture, rather, we will see power flow through the transmission line. So, we have power flow through the transmission line. We have two equations, Vs is equal to A VR plus B IR, and Is CVR plus D IR. However, only this equation will be required to discuss this power flow through the transmission line. Now these are phasors, so we assume Vs, that is equal to Vs magnitude with an angle of delta, VR which is equal to VR magnitude angle 0, because it is a reference phasor. Next we have IR. IR phasor can be written as IR magnitude at an angle of minus phi, phi being the power factor angle. A is a constant, its magnitude is A and angle is alpha. It's closely 0, however it varies, sometimes 1 to 2 degree. And for B, its magnitude is B, however angle is beta. For all practical consideration, beta lies between 75 to 85 degree. So these are all our assumptions. So complex power at receiving end, we will compute complex power at receiving end. So we have SR. So what is SR? SR should be equal to active power at receiving end plus reactive power at receiving end. SR plus JQR. Now which is equal to voltage at receiving end and receiving end current conjugate, not VR into IR, but you must consider this conjugate sign, star. So VR into IR star. So let me first evaluate what is IR. So IR should be equal to Vs minus A VR by B. So due to this Vs by B, its magnitude is Vs by B, but Vs is contributing an angle of delta, B is contributing an angle of beta, so this angle, net angle contribution, should be delta minus beta. Now similarly, this A by B by VR, its magnitude is A by B into VR, and its net angle contribution is due to A is alpha and due to B is beta. So VR is 0, so the net angle contribution is alpha minus beta. So similarly, so therefore complex power SR, which is equal to, so VR phasor into IR phasor conjugate. So what is VR phasor? So VR magnitude, it is contributing 0 degree because it is considered as a reference phasor. Now what is IR conjugate? Now conjugate means what? These angles will be reversed, just 180 degree opposite. So first term will come Vs by B. Now this angle will be beta minus delta minus A by B into VR angle beta minus alpha. So now on multiplying we get Vs into VR by B angle beta minus delta minus A by B VR square angle beta minus alpha. So this is the formula for or expression for complex power. Now complex power has got two parts. As the complex power has got two parts, one is active power and another one is reactive power. So active power, you know, the real part is the cosine component. Real part is the cosine component. So we can write PR is equal to, so therefore we can write PR is equal to Vs VR by B magnitude into cos beta minus delta minus A by B VR square cos beta minus alpha, and QR should be sine component, so that will be writing Vs into VR by B sine beta minus delta minus A by B into VR sine beta minus alpha. So these are the two expressions. Now the question comes, one question comes when PR becomes PR max. This is very relevant question. This question is very relevant because during summer we need in peak hours we need to increase or we need to maximize our active power load. So that is a very pertinent question. The answer is, with this expression you can see we have two components. One is this first component VR by B cos beta minus delta, and second component is this A by B VR square cos beta minus alpha. Now if we somehow manage to increase this term, then this PR will increase. This first term Vs by VR by B cos beta minus delta, if you somehow manage to increase this term, PR will definitely increase and it will be maximizing. So how it can be maximized? When this value will be maximum? When this value will be maximum? The answer is when cos beta minus delta is 1. The answer to this question is when cos beta minus delta, it should be equal to 1. So when cos beta minus delta equal to 0, the answer is beta should be equal to delta. So this is the condition for maximum active power. However, unfortunately, this is not practically possible. However, it is not practically feasible. Why? Because the power delivered to the load follows this curve. Power delivers to the load follows this curve. In x-axis, we have delta. In y-axis, we have P, active power. The maximum power is at this point. This is pi by 2. Now, as I already mentioned that beta, the practical value of beta is 75 to 85 degree. Okay, so if beta is equal to delta, then that delta should be operated at this point near to 90 degree. Okay. Now the problem with this is that if somehow some disturbances come like faults, this delta starts to increasing, and by somehow if this delta comes at this side, if somehow if this delta comes at this side, suppose at this point, it is very tough to bring it back, and once it comes to this side, it goes on increasing, and finally it will ultimately goes to this point. So at this point what will happen? Power becomes zero, so your entire power system will be getting blackout. So this is a very problematic, so that is why it is not practically feasible. So it is always advisable to operate your power system preferably in these locations where delta should be in between 10 to 30 degree. So even if some disturbance comes, it can get ample time to gain its original position due to some damping, natural damping or forced damping induced in the system. So that is the problem. So beta can never be equal to delta. So with this, you can see we have a active power equation and we have a reactive power equation. So under which condition a power is transferred as well as the reactive power is required at the receiving end, we shall see using a term or using a topic. It's called power circle diagram. So in the next class, with this power equations, both active power and reactive power, we shall see how the powers means reactive power or active power is needed at certain loading condition at the receiving end using a circle diagram. Okay. So with this, we are ending here. In the next class, we shall see the next topic, which is power circle diagram, which is based on these two equations. PR is equal to this and QR is equal to this. So it is the active power demand at receiving end and reactive power. It is the active power demand at receiving end and reactive power demand at receiving end. Okay. So in the next class, we shall discuss power circle diagram both analytically and graphical way. There are two approaches, analytical approach and graphical approach. I am ending with this today's lecture. Thank you.